In this lecture, we are going to discuss about Cauchy residue theorem. First is the statement of the theorem. Let fz be regular function. Let fz be a regular function except at finite number of poles z1 z2 zn within closed contour C within closed contour C and continuous in the boundary of C then integral over C fz dz equal to 2 pi I summation residue of fz at z equal to zi. I ranges from 1 to I ranges from 1 to n. That is, if fz is my regular function, that is analytic function except a finite number of poles within a closed contour C and continuous in the boundary of C, then integral over C fz dz is equal to my 2 pi I sum of residue at this finite pole. Next proof. First, we will draw this figure. This is Z1. Suppose this is Z2. This is Z3. This is Zn. Draw a circle gamma 1. This is C. This is gamma 1. This is gamma 2. This is gamma 3. Gamma n with Z1, Z2, Z3 up to Zn has a center. We should draw non-overlapping circles gamma 1, gamma 2, gamma 3, gamma n, each of radius r. So write with Z1, Z2, Zn as center and radius r. We draw non-overlapping circles gamma 1, gamma 2, gamma n lies completely inside C. Then the function fz is analytic in the region between C and gamma 1, gamma 2, gamma. Okay. Then the function fz is analytic in the region between this, that is fz is analytic in this region between c and the gamma 1 gamma 2 dot 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 gamma n. Therefore, by Cauchy integral theorem, by Cauchy theorem, not Cauchy integral theorem, Cauchy theorem, we have this one, gamma 1 fz. By Cauchy theorem, we have this one, integral over c is equal to integral over sum of integral over this gammas integral over gamma n fz dz. Okay. Now, next, suppose fz has pole of order, pole at z equal to z1 of order m1. Then, by Lorentz series expansion of the function fz about the point z equal to z1, we can write this phi z equal to psi 1z, where psi 1z is analytic in gamma 1, and this is b1 by z minus z1 plus b2 by z minus z2. By definition of pole, we know that z equal to z1 is a pole of order m1 if the principal part contain m terms. Okay, principal part in the Lorentz series expansion about the point z equal to z1 contain m terms. This is a square, this is okay, where phi 1 z is analytic within and on within and on gamma. Okay, now integrating, therefore now integrating, that is integration c fz dz, integration over gamma 1 versus gamma 1. Okay, here I'm considering fz as a pole z equal to z1 of order m1 in gamma 1. Okay, in gamma, then I can expand fz in a Lorentz series of the form this about the point z equal to z1, where phi 1 z is analytic on gamma 1. Now integrating around gamma 1, we get this one, integral gamma 1 phi 1 z d of z plus integral gamma 1 b1 z minus z1 dz plus integral gamma 1 b2 dz z minus z1 square plus dot 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 plus integral gamma 1 bm z minus z1 to the power m dz. Okay, next we are going to find out this value of this integral, but here file you should write, before that you should write this one, gamma 1 integral over gamma 1 phi 1 z1 dz is 0, because phi 1 z is analytic in this circle gamma 1, so integral around this gamma 1 phi 1 z phi 1 z dz is 0 by Cauchy theorem. Next we are going to find out this in integral gamma 1 b1 z minus z1 dz, putting z minus z1 equal to r e I theta. This implies dz will be my r I e I theta d theta. Okay. Therefore, integral over gamma 1 b1 dz is equal to z minus z1, and since b1 is free of z, so b1 can be taken outside, and this is here gamma 1 is a circle, so theta varies from 0 to 2 pi. Then put the value of dz, that is r I e I theta d theta, and this here is r e I theta. Cancel the common term, this will cancel out. So I will come outside the integral sign, and 0 to 2 pi d theta. Now this is equal to I b1 theta 0 to 2 pi, and this is equal to 2 pi I b1. Okay. Next we are going to check out what is the value of this one is equal to 0. Value of this one is 2 pi I b1. Now I'm going to check out what is the value of this one. This one, if I put, I have already found for b1. If I put m equal to 2, I will get this term. In this way, up to m by z minus z1 to the power m dz, I will get the value. So I will take the general term. So therefore, integral of gamma 1, then bm z minus z1 to the power m dz, okay, is equal to integral gamma 1 bm can be from outside r I e I theta d theta. Dz is this one. This is r m e I m theta, and this here I can become outside, can be taken outside the integral sign. Here it is rm, here it is r. If I take it to denominator, it is m minus 1, then it is 0 to 2 pi. And gamma 1 is a circle, so theta varies from 0 to 2 I pi e to the power minus I m minus 1 theta d theta. Okay. Next, here I will put this equal to t. Let minus I m minus 1 is theta is equal to t. This implies minus I m minus 1 d theta dt. This implies d theta is equal to minus dt by I m minus 1. Okay. When theta is 0, when theta is 0, theta is 0, t is equal to 0. When theta is equal to 2 pi, t is my minus t is my minus 2 pi I m minus 1. Is it? I m minus 1. Therefore, integral gamma 1 bm dz z minus z1 z1 to the power m is equal to 0 I bm mr m minus 1 0 to 2 pi I m minus 1. Now e to the power t dt, is it? Which is equal to I bm r m minus e to the power t 0 minus 2 pi I minus. So put this value I B M R m minus 1. Here it is e to the power minus 2 pi I m minus 1, then minus e to the power 0, e to the power minus 2 pi I, where k is my m minus 1. So this is also 2 pi I k plus, minus, not plus, minus sine 2 pi I k, and that is equal to my 1. So this is 1 minus 1, that will be equal to 0. So put this value, I will get b m r to the power m minus 1, 1 minus 1, that is equal to 0. So here there will be 1 m minus 1, okay? There will be 1 m minus 1 that come from here. Here, this is minus 1 m minus 1. So this is minus m minus 1. So this you should correct it. This is minus m minus 1. Okay. This is m minus 1, which is m not equal to 1. Otherwise, our value is undefined. Okay. Since therefore integral of a gamma 1 pm z minus z1 to the power m dz is equal to 0. Therefore, this integral, value of this integral is 0. This is equal to 0. So this integral is my 2 pi I b. Therefore, integral of a gamma 1 half z dz equal to 2 pi I b1. Similarly, here it is equal to b1 is the 2 pi I residue of coefficient b1 in the Taylor series expansion of fz about the point z1 is the residue of fz at z equal to z1. Similarly, gamma 2 is equal to fz dz equal to 2 pi I residue fz z equal to z2 goes on integral gamma n fz dz 2 pi I residue f of z equal to z. If I add all this up, then I will get integral c fz dz. Therefore, integral of z dz gamma 1 fz dz plus integral gamma 2 integral of gamma 2 fz dz, then the integral of gamma n fz dz, that is equal to 2 pi I residue of fz z equal to z1 plus 2 pi I residue fz z equal to z2 plus dot 2 pi I residue of fz at z equal to z. This implies integral over C fz dz is equal to 2 pi I sum over I ranges from 1 to n residue of fz at z equal to zi. Hence the theorem. With that, I would like to conclude. Remaining will be in the next lecture. Thank you.